Hi, we're from Mr. Collier's third period accelerated physics class, and our central topic for the Theoretical Thursday presentation is how can the United States federal government further explore, colonize, and travel in outer space. Our conclusion, which we'll get to in just a sec, but give you a little hint, is solar sails, as you can see. There's a central apparatus in it, and then from there, there's almost a fan-like structure that's made up of a reflective material. But we'll get that to in just a sec.
And our topic compares mostly to, or a lot to Chapter 13, which is fluids. It deals with the density of the material. So, for example, the density of the solar sail. Obviously, the lighter the material is, or the less dense it is, the more it'll be able to carry. And the chapter also deals with pressure. And so this topic we can use measure the pressure with how these solar sails work and the pressure on other planets, so different gravitational forces other than Earth.
So the first thing we want to do in our presentation is introduce what a solar sail is and how it functions. It's the physics behind what we'll get into in terms of exploring space and why these are beneficial. The first thing that we want to make absolutely crystal clear is that solar sails are not solar panels. I'm sure from the original image we showed you at the beginning, or just from connotations that you have when someone says solar power, solar energy, it's not solar panels in that like they go across the desert and they're able to absorb the sun's light. We'll prove in just a second, and Einstein originally showed this, is that photons actually create more energy and more force when they are repelled off of something than they are absorbed by almost a factor of 2. So instead of absorbing the photons, our goal is to push them off and create a force differential that allows for the sail to be pushed forward through frictionless space. So with that in mind, I figured we could start off by talking about how the sail functions. So as seen in the original picture, here's our solar sail, or at least a section of the solar sail segment of it that's going to happen. What happens from here is there are photons, as we'll represent with these like little circles, that are omnipresent all across the universe. The sun has them all the time in forms of solar, wind, or solar radiations, photons. And the solar sail can work off of either of these. The solar wind is a little less powerful than the photons in the solar radiation. And they'll come in, and a lot of them will be able to bounce off. And that's our goal with the solar sail, because we want to bounce it off as much as possible. So it goes like that, goes like that, goes like that. We'll say, because it is often a darker color, this one maybe will be absorbed, this one maybe be absorbed, and this one will go off again. Through this, the ship is able to move forward. And that's the basic principle of solar sailing. Now, this all comes from Einstein, who talked about solar radiation in the following context. He argues that the energy is equivalent to IAV over C. I know it seems a little foreign, and it should be, because not only is this new to you all, in that we're not going to talk about this until chapter 25, but it's also on the cutting edge for all science out there. And what Einstein argues is that the force of the photon is a product of the average intensity being how often it strikes, with what force it strikes, all divided by C. C equals the wavelength sign times the frequency, so how long the photon is times how often it strikes, F being the product of 1 over T, as we've just learned in this chapter. And what he concludes is that as a result of the strike, an individual photon, just one photon in the entirety of outer space, has the force of 4.57 times 10 to the negative 6 newtons per meter squared, I should say. That's a lot of energy, given how small the photon is. And that's from being absorbed. As we keep in mind, because they're repulsed off of, is because they bounce off, it's actually going to be double the energy, and we get 2 times this factor, which means it more successful. Now, Lebedev in 1900, he was a Russian physicist, came up with this idea and originally started to work with it. So the Japanese Space Agency, who tested this in 2010, all has him to thank and this physics to thank. Now, before we move on, it's important to note that you can control these sails so that they don't always just go in the same direction. This is obviously very important, just as it would be in a car. The first way is relatively obvious. Here you have the sail to this degree, this kind of structure. However, all you have to do really to change the direction is change the orientation of the sail so that the photons strike it at a different level. This means that it bounces off in a different direction, the photons do, and the sail is then propulsed in a different direction. The other way is if there's a planet nearby. So here's our big Earth. We'll kind of draw like planet there. Bad planet. But the gravitational force pulls in the ship if it gets close enough, and obviously then that changes the orientation of where the sail is going to go. So with this in mind, we're going to talk now about why these would be beneficial for NASA and the U.S. space.
So now we have to examine why sails are important for space. And so the main reason these solar sails are important in space is they're better for outer space exploration, and they don't need fuel. As Tyler talked about before, they use the photons and the sunlight and energy to power them. I remember chapter 25 mentions radiation pressure, and that's also another source of, I guess, fuel. They're green. Solar sails are green. They don't need fuel. And so now we have to examine the question of density of the ability to carry things. So our first problem would be the rocket. And so the mass of the fuel and the tanks of the rocket, just the fuel and the tanks, not the rocket. So just the fuel and the tanks, the mass of those are 1,198,157 kilograms. And the volume is 2,760 meters cubed. And so as we learned at the beginning of chapter 15, our density is mass over volume. So we just take the mass here and divide it by the volume, and that gives us our density of 434 kilograms over meters cubed. And it's 3 significant digits here because it's 3 significant digits right here. We take the least number of significant digits given. And so that's the density of the rocket fuel and the tanks. And so now we go over here for the mass of the sail. And so as we learned, the sail is given a mass of 5 kilograms for every 32 cubic meters. And so if we calculate the density, we take the mass divided by the volume, and we get 0.16 kilograms over meters cubed. And we use 2 significant digits. Those are the 5.0 kilograms and the 32 meters cubed. And so in other words, that's 0.16 kilograms per meter. No. 0.16 kilograms per meter cubed. And this material is much less dense, as you can see, compared to the rocket fuel. The rocket fuel in the tanks. So the low density of the solar sail it opens the possibility for faster and farther travel. And so, for example, Mars. So it's going to take a lot quicker time to go to Mars because there'll be a lot less weight that it'll be carrying, not as much payload. So low densities are good.
So now that we looked at the density of solar sails and the ability of them to fly in space, we do want to consider the ability of them to get off of the ground. In particular, it would be important for them to talk about how they're able to get off the ground at Earth, where we'd launch them, and other areas where we would go in possibilities like Mars or the Moon. For this example, we're going to use Mars. It should be noted that because these are more used as accelerators, there would need to be some sort of help for them to get off of the ground. But we want to talk about a little bit how it would vary in terms of how much energy would be needed to get them off of the ground based on the pressure experienced due to the column of air of the atmosphere on the Earth and Mars. So from this most recent chapter, we know that the pressure due to a column of fluid, in this case the atmosphere, equals P1 plus the gravity times the height times the density of the fluid that it is in. So for Earth, we know that the pressure of the atmosphere is 101,300 pascals plus 1,000, this would be kilograms meters cubed, times 9.81 in terms of the acceleration of gravity. And then we'll say it's a mile up in the air, so 1,760 meters. You simply multiply these together and add it to this value, and you get your final answer, which is going to be 17,366,900 pascals. For the sake of ease of showing the question, it'll be 17,370 kilopascals, a very, very large number, which explains why you need so much energy to get off of the Earth to go explore space. Now, luckily for us, on Mars it would be a lot easier because the atmosphere is a lot less dense, also because gravity is a lot weaker. So we know that the pressure is 30 pascals, remember 30 versus the 101,000, huge difference, plus the density of the fluid, which in this case is 0.02, again kilograms meters cubed, times 3.71 meters per second squared. Again, a huge difference between 9.81 and that. And we'll say again for consistency, a mile up in the air, so 1,760 meters. Again, multiply this out, add it to this, and simplifying, your answer is only going to be 16 kilopascals. This might seem a little tangential at first, but it shows the possibility of us being able to use spacecrafts and get them from Earth to other planets and be able to bring them back. Now that we've talked a lot about colonization, there is one other reason why solar sails could be extremely beneficial. They would allow us, because we saw earlier the difference between the mass of a solar sail and fuel, all that additional mass could be used to collect space debris, space junk kind of up in space. I'm sure as you've heard recently, some of broken satellites have fallen back to Earth, risking lives and risking property. Luckily, because the solar sail is able to carry so much more mass than a rocket, they could be used to collect that space debris and bring it back to Earth, preventing any kind of damage to ecosystems or damage to populations. For those reasons, we think solar sails would be very important to pursue.
Now, given the already low density of the solar sail that I calculated earlier, it was 0.16 kilograms per meter cubed. Now we have to look at how can solar sails be more effective. And so one way to do that is to make the sails less dense. Newer material, lighter material, you name it, and they're trying to match that. So NASA, for the past couple of years, NASA's been working closely with a private sector company, Legard, and they've been able to narrow the density down to about 5 to 7 grams per meter cubed. And you're probably thinking 5 to 7 grams per meter cubed, wow, that's higher than what we originally calculated. No, 0.16 kilograms per meters cubed is what we calculated earlier, but this is 5 to 7 grams per meter cubed, so there's a big difference right there. And this is definitely an improvement on NASA's older model. The new one, the 5 to 7 grams per meters cubed one, is the material's called Tanex, and it's an improvement on the Mylar, which was the 10 grams per meter cubed. And an example of an even older one, like one of the original ones that they started with, was called CP1. And so it's just showing that they're always trying to improve and update the design and make them less dense.
Okay, so obviously we've shown you a lot of the theoretical idea, be it Theoretical Thursday, but before we finish off, we wanted to let everyone know that this really is a real technology in the status quo. The Japanese Space Agency created a sail called Icarus, which in 2010 was the largest solar sail to ever be tested. It worked pretty successfully, and right now NASA is pursuing private investment. So, for example, the University of Surrey is creating something called the CubeSail. A little bit different than what we originally showed you. Instead of a fan-like structure, it's a little bit more like a kite with a boxed structure and then sails coming off of that. So there's a ton of innovation, as Connor said, in terms of density, not just with density, but also with architecture and the ability to use solar sails. It's a very real technology.